Okay, folks, here we're going to take a look at number 4 from page 145. So it's a pretty standard problem. Then we're given a rectangular piece of cardboard, 100 by 40, and they tell us to chop off 4 congruent squares from each corner, okay, in order to make an open top box. Okay, so we're going to cut these out, okay, and then this is going to be the base of our box. And then each of these 4 flaps will be turned over to create the sides of the box. Okay, and what we want to do is we want to do this so that we're maximizing volume. But of course, volume is length times width times height. Here we have a function of 3 variables, so we need to find a way to write it in terms of 1 variable. Okay, so one thing that's consistent throughout this whole problem are the squares that we're cutting out. So let's make a side length of this square equal to x. So all of these little sides are equal to x. And so now we can use that, in fact, to write all 3 dimensions. So the length is this here. Okay, so here we've got a total of 100, and we're chopping off x on either side. So this is going to be 100 minus 2x. Our width, very similar. The whole thing is 40, and we're chopping off 2x on either side. So this is going to be 40 minus 2x. Okay, and then the height of the box is just going to be the height of this flap, which just has a length of x, so times x. Okay, so here's our model, already given in terms of 1 variable, so no need to use any other constraints. So let's just figure out what the domain is going to be. Well, obviously x has to be bigger than 0. You have to actually cut out a square to get a box. Okay, and in terms of determining the highest value for x, well, let's work with the smaller side. Okay, and we realize that it's going to have to be less than half this side length. Because if it's exactly 20, then I would just be folding the sheet in half. But I need to have a bit of a width here. So this has to be less than 20. So there's our domain. Now we do notice here that it's not a closed interval. Okay, so we're going to have to deal with that. This is just a cubic, so let's start by multiplying it out so we can take the derivative easily, because that last thing I want to do is use the product rule twice here. Okay, so let's distribute this first one here. So 100 times 40, that's, whoops, 4,000. Okay, so here we have minus 200x minus another 80x, so minus 280x. And then here we have negative 2 times negative 2 is plus 4x squared, and all that times x. Okay, so we've got v is equal to 4x cubed minus 280 x squared plus 4,000. Okay, and first thing I'm going to do, simplify my life, is let's at least factor out a 4 here, since that's factorable on all 4. So here 4, so we've got x cubed, 280 divided by 4, 20 divided by 4 is 70, so this is 70x squared plus 1000x. Okay, and now we can take the derivative, and what's great is that this 4 is just a constant, so it does not affect taking the derivative. So I'm left with 3x squared minus 140x plus 1000. Okay, and here, well, there's nothing to factor out in this here. Okay, so we need to find our critical points, so make that equal to 0. I'm not even going to try to factor this as 2 binomials, so I'm just going to go straight ahead and use the quadratic formula. So x is equal to negative b, so 140 plus or minus, so b squared, which is 140 squared minus 4 times a times c, okay, all over 2a. Okay, so let's simplify this a little. Okay, so what do we got here? We've got 140 squared minus 4 times 3 times 1000. Okay, so this is 140 plus or minus root 7600 over 6. Okay, and this is an application question, so right off the bat, I'm just going to find approximations. So 140 plus square root of 7600. Okay, and divide that by 6. And we see 37.86. So already we know that's not going to count. That's too big. Okay. Our other option here is 140 minus the square root of 7600. Okay, divided by 6. Okay, 8.8, and that does fall within our range. Okay. So we need to make sure that this is indeed a maximum and that it's a maximum in that interval 0 to 20. So we're only interested in 0 to 20. Okay, but here remember that one of our zeros for the derivative is at 8.8. Okay, and the other one was all the way at 37.86, and the derivative was a quadratic opening upwards. Okay, so here we're going from positive to negative. Okay, and we see that as we're going from 0 to 8.8, the function will always be increasing, and as we go from 8.8 to 20, it'll always be decreasing. So 8.8 is indeed that value that we're looking for. Okay, so let's just take a look at what the question actually asks. It says calculate the dimensions. So excuse me. So we know the height is going to be equal to 8.8 centimeters. The length is, that one is 100 minus 2 times x. So minus 2 times 8.8. So here, 100 minus 2 times 8.8. So 82.4 centimeters. And the width is 40 minus 2 times 8.8. So that's, the width is going to be 22.4. Okay, and there you have it. There are the dimensions that give you the open top box with the largest volume.